Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss about the mobility, conductivity and donor and acceptor states of semiconductors. The topic on mobility and conductivity are meant for class 12 students of CBSE, ISE and different state boards. This will also be found useful for JEE mains and NEET aspirants. The topic on donor and acceptor states are meant specifically for BSc Physics and Electronics students. The complete note of the topics are given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. We now see what is the mobility of charge carriers. So when we apply an electric field across a crystal, the charged particles, whether they be electrons or whether they be holes, they begin to move under the influence of the applied field. Higher the applied field, higher will be the velocity acquired. So we can say that the velocity acquired by a charged particle in an electric field is proportional to the magnitude of the applied field. If v be the velocity acquired by the charged particle under the influence of an electric field E, then we can write v proportional to E or v equal to mu E, where mu is a constant known as the mobility of charge carriers. Okay? Now, mu can be written as v upon E. Okay? V is measured in meter per second, whereas electric field is measured in volt per meter. And therefore, the unit of mu or the mobility will be meter square per volt per second. Clear? So in equation 1, if we put E equal to 1, okay, so we have seen that mu equal to V upon E. So if we put E equal to 1, then what we get? We get mu equal to V, isn't it? So mu is numerically equal to the velocity acquired per unit electric field. यूनिट फील्ड लगाने से जो वेलोसिटी चार्ज पार्टिकल एक्वायर करता है उसे हम बोलते हैं मोबिलिटी. सो इक्वेशन 1 से ये फॉलो करता है कि चार्ज पार्टिकल इन एन इलेक्ट्रिक फील्ड drift in a given electric field with a constant velocity, which however is not correct. इसमें गलती क्या है भाई? गलती ये है that when we apply an electric field, each charged particle in the crystal is accelerated, and after traversing a short distance, suffers a collision with other charged particles. At each collision, it loses most of its velocity it has acquired, and then it starts to accelerate once more under the influence of the applied field. This process is repeated, and when all the mobile charged particles having similar charges are taken into account, the average velocity is given by equation 1. The value of mobility depends upon many factors such as temperature, purity of material, and the type of impurity added. For germanium and silicon, the mobility of electrons in the conduction band is more than that of holes in the valence band. So mobility of the charged particles in the conduction band and valence band. We have seen that the electrons move in the conduction band and holes move in the valence band. तो दोनों की मोबिलिटी में अंतर है even though the applied field is the same. So why this is so? This arises from the fact that the electrons in the conduction band are more free of the attractive forces of the nuclei than are the positive holes in the valence band, which moves only as a result of the slower drift of electrons in the covalent bonds. ठीक है? इसको हम ऐसे भी देख सकते हैं. देखिए, ये हमारा सेमीकंडक्टर है, ये आपका वैलेंस बैंड है, ठीक है, ये आपका कंडक्शन बैंड है, and the two bands are separated by a forbidden gap of width delta E. At absolute zero, the conduction band is entirely empty and the valence band is completely filled up. When a small amount of energy is supplied, a few bonds in the valence band break down, the electrons are liberated, which move to the conduction band, leaving behind holes which behave as positively charged carriers in the valence band. So these liberated electrons move in a relatively empty conduction band. So they are more free to move. They freely move in the conduction band. Whereas there are few holes there in the valence band. Okay? So most of the covalent bonds are complete in valence band. So there is very few vacancy for the hole movement in valence band. Therefore, holes in the valence band cannot move as fast as the electrons move in the conduction band. And therefore, the mobility of electrons, okay, is more than that of the holes. Okay. Next comes conductivity of a semiconductor. So assume that we have a semiconductor which has an electron density n in its conduction band. इलेक्ट्रॉन डेंसिटी n है, इसका मतलब the number of electrons per unit volume in the conduction band of the semiconductor is n. If E be the charge carried by each electron, then the charge per unit volume available for conduction is n into E. Now let us find out what is the current density if you apply an electric field E. Okay? So see, assume that we have a cylinder of this area A. Okay? V is the velocity of the electron when an electric field is applied. So in time delta t, the electrons will cover a distance V into delta t. So this is a cylinder of volume V into delta t into A. Clear? So this is the volume of the cylinder. The total charge enclosed within the cylinder is then Q equal to charge per unit volume, that is N into E, and the volume of this cylinder, that is capital V. So the current is defined as the rate of flow of charge. So current is Q upon delta T. So this is N E small v delta T up into A upon delta T. So this delta T cancel out. This is N E V A with area of the flat face of the cylinder. So the current density is I upon A, current flowing per unit area. So this is simply NEV. Okay. So this is what we have written here. Because this is for electrons, we have given a suffix here, N. So the current density for electrons is Jn is NeV. And the conductivity of the material. How to find the conductivity? We have seen here that J is equal to NeV. And V in terms of mobility is given as mu into E. We have seen this one. Okay. So J upon E is Ne into mu. Clear? Now, see what will be E upon J. This is J upon E is Ne mu. See what will be E upon J. E is electric field. So this is if V be the potential applied upon L. Okay, electric field is this. Current density is I upon A. So this is V upon I into A upon L. Clear? V upon I, voltage by current is nothing but the resistance. This is equal to R. This is A and this is L. So R A upon L. So this is, we have seen earlier in our school level class that R, resistance of a conductor, is equal to rho L upon A. Clear? So 1 upon rho is 1 upon, this is resistivity. 1 upon resistivity is conductivity. So conductivity is G upon E. So G upon E is Ne mu. Clear? So this is what we have written here. Now, sigma n, that is the conductivity of the material due to electrons in the conduction band, is Jn upon E, and put the values here. So when this simplified, gives you sigma n equal to Ne mu n. Okay? Where the subscript n applies to the effects associated with electrons in the conduction band. Clear? So by similar argument or similar reasoning, we can show that if P is the density of positive holes in the valence band of a semiconductor and sigma P be the conductivity due to the positive holes, then we can write sigma P is Pe mu P. The total conductivity of the semiconductor is just given by the sum of the conductivity due to the electrons and that due to the positive holes. So sigma is sigma P plus sigma n. So this, when simplified, is put in this form. E times within bracket P mu P plus N mu N. We have earlier seen that the number of electrons and the holes in an intrinsic semiconductor are always equal at all temperatures. And therefore, we can write P equal to N equal to Ni, where Ni is the intrinsic density of electrons or holes in the material. Equation 6 can then be expressed as sigma equal to Nie within bracket mu P plus mu N. Clear? Next, we come to donor and acceptor states. We have earlier seen that when a small amount of certain impurities is added to an otherwise pure semiconducting crystal, its conductivity changes radically. If we add group 3 atoms to germanium or silicon, we get p-type semiconductor. If we add group 5 impurity atoms to germanium or silicon, we get n-type semiconductor. So when a few atoms of group 5 element, such as phosphorus, are introduced into a pure germanium crystal, 4 out of its 5 valence electrons are shared with 4 adjacent germanium atoms, forming covalent bonds. This we have seen earlier. Okay? The 5th valence electron, however, does not take part in this binding process and is loosely bound to its parent nucleus by a small binding energy. The energy state corresponding to this 5th electron lies in the forbidden gap of pure group 4 substance just below the conduction band as shown in figure 1. ऐसा हम क्यों कहते हैं कि this lies just below the conduction band? ऐसा क्यों कहते हैं? Just below the conduction band. ऐसा इसलिए कहते हैं कि 5th इलेक्ट्रॉन जो है ग्रुप 5 इम्प्योरिटी एटम का, वो लूजली बाउंड है पेरेंट न्यूक्लियस के साथ, और थोड़ी एनर्जी मिल जाए, it will become available to carry current in the conduction band. तो थोड़ी एनर्जी चाहिए इसको, थोड़ी सी एनर्जी चाहिए, a small amount of energy, and therefore its energy state lies just below the conduction band of the group 4 substance. ठीक है? ये देखिए आपको हम फिगर में दिखा रहे हैं यहाँ पर in figure 1. This is the conduction band, this is the valence band which is completely filled up, this is the forbidden gap, and this is the energy state of the extra electron donated by group 5 atom. यही एनर्जी है ग्रुप 5 एटम की. थोड़ी एनर्जी देंगे तो यहाँ से चला जाएगा टूट के कंडक्शन बैंड में, इलेक्ट्रॉन फ्री होकर चला जाएगा वहाँ, एंड इट विल देन बी अवेलेबल टू कैरी द करंट. ठीक है? यहाँ देखिए, थोड़ी एनर्जी उसको दे दी गई, इट इज गिवन सम अमाउंट ऑफ एनर्जी फ्रॉम एनी एक्सटर्नल सोर्स. तो ये इलेक्ट्रॉन जो है उससे डिटैच हो गया, डिटैच होके इट गोज टू द एम्प्टी कंडक्शन बैंड where it becomes free to carry current, and this becomes positively ionized donor state, which is just below the conduction band of the n-type semiconductor. ठीक है? अब आइए आगे देखें। Since each group 5 atom donates one electron to the conduction band, adding a few impurity atoms to an intrinsic semiconductor increases its conductivity appreciably. For example, at room temperature, adding one atom of phosphorus to 10 to the power 8 atoms of germanium increases its conductivity by a factor of 12. ठीक है? Similarly, each group 3 atom introduced into germanium crystal creates a hole. The energy state introduced into the crystal by the group 3 atom lies in the forbidden gap of group 4 semiconductor just above the valence band and is known as acceptor state. This is shown in figure 3. तो देखिए ये फिगर 3 हमारा है। जब हम डालते हैं ग्रुप 3 के एटम को मिलाते हैं एज इम्प्योरिटी तो क्या बनता है हमारे पास? हमारे पास बनता है फिर पी टाइप सेमीकंडक्टर। इसका एनर्जी स्टेट जो है इम्प्योरिटी एटम का वो फॉरवर्डिंग गैप में होता है और वैलेंस बैंड के ठीक ऊपर, सो दैट even if a small amount of energy is given to it, this accepts one electron by breaking equivalent bond in the valence band. So this becomes now negatively ionized and we have a hole in the valence band. ठीक है ना? कैसे बनता है इलेक्ट्रॉन होल पेयर ये आपको हम पहले बता चुके हैं। सो एनर्जी स्टेट है, ठीक है, इसमें एक इलेक्ट्रॉन कमी है, थोड़ी एनर्जी मिलेगी तो यहाँ से बॉन्ड को तोड़ेगा, वैलेंस बॉन्ड को तोड़ता है, कोवेलेंट बॉन्ड को यहाँ, और इलेक्ट्रॉन चला गया जंप होकर इसमें, तो ये हो गया आपका निगेटिवली आयोनाइज, और एक यहाँ इलेक्ट्रॉन कमी हो गई तो ये हो गया आपका पॉजिटिव होल। नाउ दिस पॉजिटिव होल नाउ मूव्स इन दी वैलेंस बैंड। ओके, as there is no corresponding hole in the conduction band, only the whole motion in the valence band contributes towards conductivity. When the group 3 atom accepts one electron from the valence band, it becomes negatively ionized, but the negative ion remains fixed in the crystal lattice and hence cannot move under the influence of an electric field. ये देखिए फिगर दिखा रहे हैं आपको हम कैसे आयोनाइज होता है। ये देखिए ये कंडक्शन बैंड है, ये वैलेंस बैंड का टॉप है, वैलेंस बैंड भरा हुआ है, दिस इज द फॉरवर्डिंग गैप। हमने एक इम्प्योरिटी एटम मिलाया है उसमें ग्रुप 3 का, कोवेलेंट बॉन्ड टूटता है, वो चला जाता है इस एनर्जी स्टेट में, तो दिस बिकम्स द एक्सेप्टर एटम नाउ बिकम्स निगेटिवली आयोनाइज्ड। और यहाँ क्या बच गया? यहाँ बच गया पॉजिटिव होल, इलेक्ट्रॉन चला गया टूट के ऊपर, पीछे क्या छोड़ दिया? ये होल विच बिहेव्स एज ए पॉजिटिवली चार्ज पार्टिकल इन द वैलेंस बैंड। ठीक है, so this is the situation there. So this is all about the mobility, the conductivity of a semiconductor, and what are the donor and acceptor states and what is their position. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें। So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.